Before we get too much further into this course on environmental science, we certainly need to discuss what science is. What do you think? When you hear the word science, what comes to mind? For many people, they think of a mass of knowledge and facts. Many textbooks focus on the process aspect of science. I have some definitions right here. A method of knowing, or a systematic process used to investigate the natural world, or a human endeavor to discover and better understand the underlying patterns in nature and use the knowledge to make predictions, solve problems, and provide new insight. Wow. Personally, I like your book's definition. A body of knowledge and the process used to gain that knowledge. Indeed, it's both. Our book definition is good, but there are a few other important points to be made regarding science. First, science focuses on studying and explaining the natural world. This is the domain of science, the natural world. We can use science to understand and explain the world around us. We cannot use science to explain the supernatural and/or questions outside of the natural world around us, such as, what is the meaning of life, or does the soul exist? Second, science relies on observation and evidence. Science assumes that the world is consistent and predictable, and scientists attempt to reduce this apparent complexity of the world into general principles that we can use to make predictions. Through careful data collection, observation, experimentation, and analysis, scientists draw conclusions about the natural world. These conclusions are inferred from data, not based on faith, intuition, or emotion. Notably, religion and cultural stories and art are other ways that people in society study the natural world and our place in it. However, these practices rely heavily on faith, intuition, and/or emotion, rather than empirical evidence. Third, science uses testable ideas. Your text does a good job of elaborating on this concept, but basically a scientific hypothesis must be testable. This means it must generate expectations or predictions of what we should observe if it is true. Further, these predictions must be falsifiable. There needs to be a way to prove them incorrect. Ideas that are not testable cannot be investigated by science. Fourth, science involves the scientific community and leads to ongoing research. Science is not an individual endeavor. A vital step in the scientific method, which we'll cover in a minute, is the sharing of new knowledge with other scientists. Scientific findings must be repeatable by other scientists, and the findings are also published and critiqued in peer-reviewed literature. In this manner, scientific findings are self-correcting over time, and bias or error can be reduced, or hopefully eliminated. Lastly, science does not prove things. What? Really? Yes, it's true. Science does not prove things. Science is an ongoing process, starting with uncertainty and leading to less uncertainty. Notice I say it leads to less uncertainty and not certainty. Science does not prove things. In this manner, no scientific conclusion is ever completely final. It is always open to revision. This, in fact, is one of the strengths of science. Let's look at infographic 2.2 from your text. We start with complete uncertainty. We're clueless. And then through the process of science, we begin to gather evidence and we gain certainty. We never get to absolute proof. That's not in the realm of science. In fact, science is really good at disproving things. It's not so great at proving things. Notably, some uncertainty does not mean that scientific conclusions are invalid. In popular media, you often hear non-scientists criticize scientific findings by claiming they can't be proven to be true. These types of claims suggest that the person making the claim doesn't really understand science. As an example, science cannot tell you that you will, for sure, get lung cancer if you smoke, but that does not mean that there is not a strong correlation between smoking and lung cancer. Further, the scientific evidence might spur you to take some action if you're a 2-pack-a-day smoker, even if we can't prove you'll get cancer. In the popular media, you also often hear people use the word theory incorrectly. You may hear some media pundits say, "Scientists say it's just a theory." Well, in science, a theory is widely accepted, and it's been extensively and rigorously tested, and it's never failed a test. Also, generally, a theory brings together many different hypotheses into a unifying concept. Indeed, theories are very close to absolute proof, or at least as close as we're going to get in science. So why is science never 100% certain? Well, basically, science is good at proving things wrong, but it can never prove something 100% true because it's impossible to test every scenario. Your book did an excellent job of explaining the scientific method as it followed the story of how we figured out what was happening to stratospheric ozone. This infographic here also visually shows the scientific process, or the scientific method. We all learned it in middle school and high school that we make an observation, we develop a hypothesis, we design and carry out experiments, then we analyze our data, draw conclusions, and report our results to the scientific community. In that way, it really does seem like a linear process as you're moving through. But I want to stress here that science is not a linear process. And this diagram shows that to some extent. At every step along the way, there's often a circling back that occurs, especially in the sharing with the scientific community. Scientists routinely encounter unexpected results or unexpected problems during their experiment that require revisions of their hypothesis or the creation of new experiments. Indeed, experiments that fail often provide invaluable new knowledge and a whole set of new questions. And the observations and sharing that occur among the scientific community occur throughout the process and also lead to new ideas and new hypotheses. Another point that I'd like to make is that science is a highly creative process. The best scientists are often those who can make interesting observations, ask creative questions, or see results from unique perspectives, and or blend seemingly unrelated fields of study together. Science is exciting, creative, and often full of a sense of adventure. When we chronicle the scientific method in 5 steps, we don't get a sense of that creativity that's necessary in the scientific process. Science plays an important and vital role in creating a more sustainable world. However, science is only part of the process used to address environmental issues. Sound science alone will not solve anything. What else needs to happen? I've pasted in some steps for addressing environmental problems here. Pause the video a moment and check them out. Notably, these steps don't always occur in a linear manner. Sometimes public education and involvement or political action may be needed to identify a problem and spur scientific assessment. In fact, the importance of public education and involvement, as well as political action, cannot be overemphasized. As responsible citizens, we need to get involved. An underlying goal of this class is to build awareness about local, regional, national, and global environmental issues, to connect you to resources, and to encourage you to get involved. Science is a valuable tool that can be used to solve environmental problems and help create a more sustainable future. But people need to be educated and involved in order to maximize our use of this tool. Notably, political action is hopefully based on sound science. However, often there is still disagreement on the best course of action, even when the science is well understood. Sometimes these disagreements occur because lawmakers don't understand the science. Further, disagreements often stem from economic, social, or political considerations rather than scientific evidence. As we discussed in our last topic, short-term economic or political gain sometimes obscures the science or seems to trump greater long-term societal benefits. As we just noted, there is often disagreement on the best course of action. On one side, you may hear those who don't understand science saying that we need to wait for proof. Remember, science does not prove things. On the other hand, you might hear folks wanting very stringent laws enacted immediately. How much evidence do we need to make a decision? That leads us to our last concept, the precautionary principle. The precautionary principle is not a new idea. Perhaps you've heard the saying, an ounce of prevention is worth a pound of cure, or better safe than sorry. The idea is simple. It's generally better to prevent a problem than to have to deal with severe adverse consequences. In Europe, this concept is referred to as prudent avoidance. And notably, it is used much more in Europe than in the United States. As noted in your text, the precautionary principle states action should be taken when there is a chance that serious consequences might occur, even if there is still uncertainty. This suggests that when a technology or product is suspected of threatening human health or the environment, precautionary measures should be taken, even if there is scientific uncertainty about the scope of the danger. The technology or product should not be introduced or continued until it can be demonstrated that the risks are small and that the benefits outweigh the risks. For some, the precautionary principle seems like common sense, especially since scientific-based risk assessment cannot keep up with the development of new technologies and products. Thus, this principle puts the burden of proof on the developer of the technology or product. They must show it is safe instead of the public having to show it is unsafe after it's already been introduced. As you can imagine, the developers of these new products and technologies or drugs are often against invoking the precautionary principle, as it might delay the use of these new things. Further, assuring a new product or technology is completely safe is likely to be quite expensive, perhaps unnecessarily so. Occasionally, some scientists may also be against using the precautionary principle, as they may feel it challenges the role of science. Also, the precautionary principle is sometimes seen as a cover for economic gain, for example, to protect specific industries or markets. For example, the beef industry in the United States felt that the European Union's ban on U.S. and Canadian beef was simply a matter of protecting their own beef industry rather than real concerns about hormones used in U.S. and Canadian beef production. There are many examples of the precautionary principle in use, and I encourage you to find some of these examples. Your book used the example of the Montreal Protocol using the precautionary principle before all the science was clear. You may also find some instances of the precautionary principle being used with genetically modified organisms, with electromagnetic radiation, with nanotechnology, etc. Basically, any new, fast-moving type of technology where the development of the technology has outpaced the science of risk assessment is where you're likely to find the precautionary principle being invoked.